All right, AP Chemistry guys, I'm getting a setup here for the Chapter 19 stuff. I'm going to try to get through this very quickly for you here, and so I won't be doing practice problems for every single problem that's available. I do have an answer key made, and that'll be available for you in class if you'd like to look at that. First, the learning objectives. That first one, the redox stuff, that's review. Stuff that you have to be able to do to be able to work on this unit, not stuff that you are going to be tested on or quizzed on. So we have the three different objectives, galvanic cells, and we have the relationship between delta G, the cell voltage, and the equilibrium constant, and then we have the electrolysis stuff. So let's go through this. Here's learning objective 0 that we're going to skip through, and then learning objective 1. There's some repeat questions in here, notice, and that is, okay, we'll just skip over those when they come up. We have terms, the anode, cathode, the cell. Anode's where the oxidation occurs, loss of electrons. So we talk about this in terms of a waterfall. That's the analogy that we use. And so the anode is the top of the waterfall. This is where the electrons originate, and then they flow to the cathode, which is the bottom of the waterfall. So if we think about a waterfall having a top and a bottom, and the water flowing from the top to the bottom, we have the same thing here in terms of electrons going from the place that has a higher potential to a lower potential. The cell is that thing that is allowing these electrons to transfer. So when we put two different things together that have a difference in potential, those electrons can flow from one to the other, and that's going to be called the cell. The voltage is what we use to measure it. Electromotive force is what we use to calculate it. This is also called the cell voltage, cell potential, and several other things there. Then we have the standard reduction potential, which is the tendency for something to be reduced. This is how likely and it's based off of what's called the standard hydrogen electrode, which we don't get into, but that's the 0 that we use. So if something has a greater potential to be reduced than hydrogen in this She, then it will more likely be reduced. If it has a lower, it's more likely going to be oxidized. Galvanic cell, this is a repeat. Why does the electron current flow from the anode to the cathode? This is also a repeat. The anode is going to be the thing that has the higher potential for electrons to be oxidized, so lost. The cathode is going to be the place where they have a higher potential to be gained. And so they go from the thing that has the greater chance for them to lose to the thing that has the greater chance for them to be gained. Currents measured by voltage. These are the different terms that are used to describe the cell voltage. And then the standard reduction potential is another repeat from just above. So number 7 is a conceptual problem that kind of organizes this stuff in terms of like that waterfall scenario. As you go up the standard reduction potential table, electrons become stronger oxidizing agents, which means they're more likely to be reduced, which means that they're going to be the anode. I think I have that. Oh. Standard reduction. So as you go up, they're more likely to be reduced. If they're more likely to be reduced, then the cathode. Yep, that's perfect. Thought I had things backwards there for a second. This is the confusing part, where we have things that are reduced. That's the oxidizing agent. So there's some language there that we have to be aware of. This is the verb, or the oh man, my grammar. So this is the thing that is doing the work on something, and this is it being done on it. So it's being reduced, it's oxidizing something else, and that makes it the cathode. Then we could write a similar statement for going down the periodic table. Then it's the reducing agent, more likely to be oxidized, and therefore it's going to be the anode. So here we have some practice problems related to the cell voltage. And when we go through this work in learning objective 1, it's very important for us to write down these half reactions and identify what's being oxidized, what's being reduced, what's the cathode, what's the anode, so that we can organize that information in our head before we just start applying it in learning objective 2 and 3. All right, so Here is the cell. We have lead, we have lithium. There's lead and lithium. This isn't balanced. There should be a 2 here, and a 2 there, and a 2 there. But these are just the half reactions. If we wanted to rewrite them as a full reaction, maybe I'll do that real quick for you. We would end up with, let's see here. What's down below? Oh, so it is down here. So I'll just scoot down here and do the work here. The anode is the one with a lower reduction potential. That's going to be lithium. So that's the one that gets oxidized. The cathode gets reduced. That's going to be the lead. So if we have lead being reduced, we end up with Pb2 plus 2 electrons. Gets us to Pb solid. And then we have the lithium, which is going to get oxidized. We have lithium goes to lithium plus 1 electron. Now we're going to balance this thing. So the electrons cancel. So we end up with those electrons canceling. Add them together. We end up with that overall balanced equation. So we have the anode, the cathode. Once we have all of this stuff conceptually down, then we can start doing the math. Which will look like number 6. We have the cathode minus the anode, negative 0.13 minus negative 3.05. These values come from the standard reduction table. That's the handout you got in class, or it's a table in your textbook. This is the cell diagram. The cell diagram is going to have the anode listed first, the cathode listed next, and just describing what happens. So we have lithium solid going to lithium with a positive 1 charge, lead positive 2 to lead solid. This is going to be our salt bridge, and these are our phase boundaries. There's the potential, 2.92 for the final, and then you can make up a couple of your own. All right. Now we get into some work related to whether or not a reaction would be spontaneous. To do this, we can't use the table to determine the cathode and anode. Instead, we have to use how the reaction is written. So fluorine goes from fluorine with no charge to fluorine with a negative 1 charge. That means that it is going to be reduced. It's gaining those electrons to have that negative 2 charge. Negative 1 charge, which is the cathode, or magnesium goes from solid magnesium to magnesium with a positive 2 charge. So we go there, 2 electrons are being lost, so we end up oxidized as the anode. So we can actually just go to the table and look at if this matches what we would expect for them to be. Since fluorine is higher up on the standard reduction table, we would assume it to be the cathode, and that is what happens here. We can prove this by doing a calculation, and that calculation provides us with a positive cell voltage. That positive cell voltage tells us that it is a spontaneous process. For the next problem here, we have the opposite. We have the strontium being reduced, which is going to be opposite of what we would normally see in a spontaneous process if we were just running a galvanic cell the way it is. But because it's written this way, of gaining 2 electrons, it will be reduced. So there's the reduce, which makes it the cathode. So if it's the cathode, we'll take that minus the anode. We end up with, the cathode minus the anode, we end up with a negative voltage. So that provides us with information to say that this is not a spontaneous process. It is spontaneous in the reverse direction. Quickly look at those. Give you just a second to pause. I'm going to move on. Some other pieces of information related to galvanic cells, the salt bridge, and then the cell diagram. We've talked about the cell diagram and how it is built, and really it's the conventional method to show the different pieces of a galvanic cell. We have the anode, we have the cathode, we have the phase boundaries because we have the solid versus the aqueous, and then we have the salt bridge that connects them. The salt bridge allows the process to continue. So without the salt bridge, the charge balance would not be maintained throughout the process of the electron transfer from the cathode to the anode, or the anode to the cathode, and therefore the galvanic cell would slow and then stop. Now, the salt bridge does not allow it to run indefinitely. It just allows it to run until the electrons, or the ions, the positive and negative ions from the salt bridge run out. So it can maintain that balance, that charge balance, for a certain amount of time, and then it will die. All right. Now we're looking at calculating these things and writing the cell diagrams. We're just going to go to the standard reduction potential tables, look up the different values, cathode minus anode, make sure you're identifying the cathode and anode correctly. Since copper gets reduced here, +2 to nothing, it is the cathode. Since magnesium gets oxidized, it's the anode. So we have 0.15 minus -2.37. We end up with 2.52. So we can see all those. Number 14, predict if it's spontaneous or not. And for these, I actually didn't do calculations for these. It didn't tell me to, and so I just used the reduction table. So since cadmium is higher up on the reduction table, or it has a larger reduction potential, it would be reduced in a spontaneous process. So that makes sense, right? A higher standard reduction potential should be reduced if it's spontaneous. Reduction potential, reduced, spontaneous. It is, therefore spontaneous. The opposite would be true for the next one. Bromine has a higher standard reduction potential, and therefore it would be reduced in a spontaneous process. But in this case, bromine is oxidized. Since it doesn't match, it's not going to be spontaneous. We could do the calculations for these to prove it. This is going to come out with a positive value. This is going to come out with a negative value. And we can do that extra work if we want, just to make sure. And we can see the next two. Pause because I'm moving on. All right. And then we have learning objective 2. Now this is where I could no longer really type the math. So now you get to deal with my handwriting. This is where we start relating Gibbs free energy, equilibrium. So equilibrium is the equilibrium constant. Gibbs free energy is thermodynamics. Electrochemistry is going to be the cell voltage. We can identify, or we can relate all three of those together by the three different equations that we have in our triangle that we put into our notes. I'm not going to write those out. I am just going to use them here. I think we have blue. We can do that. So magnesium gets oxidized. Zinc gets reduced. Here's oxidized. There's reduced. Sorry that it's hiding up there. But we have here, that means that magnesium is going to be the anode. Zinc is going to be the cathode. We take the cathode minus the anode. It means that the cell voltage for this thing is going to equal negative 0.76 minus a negative 2.37, which is going to be the magnesium. So we have that, which means that the cell voltage here is going to be a positive value. It's written in a spontaneous way. We end up with 1.61. So the equation that we use is this one. Cell is equal to 0.0257. That's that whole mess of constants that are put together over 2, because we're transferring 2 electrons. So we 2 electrons are being lost by the magnesium and gained by the zinc. So we have the natural log of 1.61. So the cell voltage of this thing is going to equal, oh, whoops, I apologize for that. I messed up. That means that we're going to be plugging this in. That was my fault. Apologize. We are solving for the K. And this goes away. That's the 1.61 there. So now we can solve for k, rearrange, do your math. K is equal to 2.6 times 10 to the 54th. And remember, the equilibrium constant values are unitless. All right. Next one is just backwards. We're given the K and asked to solve for the cell voltage. We could actually just go to the table, the standard reduction potential table, and do that. But I'll tell you this, on the AP test, you actually don't get that standard reduction potential. On the test you take in class, you will. But that would be like you would get this kind of a problem and not have the table to basically cheat and get the answer a different way. On a problem like number 15, the values that you would need for the standard reduction values would be provided to you in the problem. So here we have the cell voltage. What we're trying to find is going to be, again, that 0.0257. This is over 2 again. It's just kind of a very common number of electrons that are transferred. So we have natural log of our K, which is going to be 2.69 times 10 to the 12th. Rearrange, rewrite, all that good stuff. We end up with the cell voltage of this thing is equal to 0.368. Now this does have a label, volts. And we could actually double check this. We could go to the table and just do the subtraction of those two things and determine if that's correct. But I'm not gonna use the time for that. Number 17 is going to be just like number 16. So I don't think I'm going to work on any of these here. Yeah, they all are, well, that number 3 is kind of messy, so maybe I need to look at that. But this one here, the end answer is going to be 1.8 times 10 to the 18th for K, and this one is going to be 2.8 times 10 to the 9th. And I think I had something in my notes somewhere about making sure you use the right cerium. I'm not sure if that's this problem or not, but you want to make sure that you use the correct cerium, +4 to +3. Number 3 is the one that looks difficult. It is not. So let's get that up here. It looks difficult because there's lots of different pieces to this reaction, but only one thing is going to be oxidized, only one thing is going to be reduced. One is very obvious. We go from iron +2 to iron +3. This thing lost an electron, so it's oxidized. That means it's going to be the anode. The other one is this right here, the manganese. Oxygen stays at -2, -2. Hydrogen stays at +1, +1. The only thing left is the manganese. It goes from 7 to +2. So in order to do that, it had to gain 5 electrons. So we end up with a reduced, and that's the cathode, but it gained 5 electrons. That's going to be important to us when we do the math on this guy. And then when we look up this stuff in the reduction table, we find that this reaction right here is one of the ones that we can look up. And that has a standard reduction potential of 1.51. Let me double check I read that right. That's reduced, that's cathode, 1.51. Yep, and so the cell voltage of this thing is equal to 1.51, which is that whole thing, that's the cathode, minus the iron, which is 0.77. Make sure you're using the correct iron. Ends up with a voltage of 0.74. And now we go through the process, plug it in, and we end up with a value of for K is equal to 3.35 times 10 to the 62. These are very large case because these are spontaneous processes. They're gonna have most of their stuff on the product side. All right. Calculate delta G and equilibrium constant. These have actually two different parts to them. Split that up. The first one is going to be our delta G part, and the other part is going to be our K. Remember that we have that triangle that allows us to relate Gibbs free energy to the cell voltage, the equilibrium constant to the cell voltage, and the Gibbs free energy to the equilibrium constant. So there's a lot of different ways you can do this problem, but the first thing that we have to look at is this. In F the standard cell voltage, and this is going to be a negative value. So to find delta G, we have 2 electrons being transferred times 96,500 times the voltage of the cell, which comes out to be 2.74. We have the cathode, which is going to be the lead. We have the anode, which is going to be magnesium. Cathode minus anode gets us 2.74. So then the final delta G value is negative 528,820 joules, or negative 528 kilojoules. All right, and now we have the other part. We can use two different methods. We could say delta G is equal to negative RT ln of K, or we could say the cell voltage is equal to 0.0257 over N ln of K. And in my notes, I actually did this both ways, and they come out with the same answer. The way that I'm going to show you is with the cell voltage here. So I'm going to do it this way. So we end up with 2.74 is equal to 0.0257 divided by 2 again. There's that 2. And then ln of K. Do your math, rearrange. K is equal to 4.98 times 10 to the 92nd. Goodness. So there is our answer there. That is a terrible 9. All right. So there's that. Now, the next 3 problems are identical. And so I'm not going to go through those, and even I didn't do all of them on my work. And so I can give the answers for number 2 that I have. K is equal to 1.8 times 10 to the 18th, and delta G is going to equal negative 104 kilojoules. So there's that. 3 and 4 I didn't even do. All right. Now we get to the Nernst equation. So we have a couple of these that we are just asking for the Nernst equation to be written out. So we have, I'll do the first one. The voltage of this cell is going to equal the standard voltage. That will equal, or excuse me, be minus 0.0257 because of all those constants again over N. Ooh, I guess we're writing this out, aren't we? So this is going to be over 2. Then we have natural log of the magnesium concentration over the tin concentration. And there we have it. Products over reactants, get rid of the solids. They don't belong in an equilibrium expression, products over reactants. So there we have it. This one here is going to be all the same thing, only we're going to be, oh shoot, I forgot to do this in class. This needs to be changed. This is a positive 2 here. There's another mistake too. Oh, all right. I guess it's done. Well, hopefully you came to the video when you got lost on this problem and couldn't figure out why there was a 3 there. And now we have it. All right, so we have everything the exact same, only it's 0.0257 over 6 electrons. Natural log of the chromium raised to the second power over the lead raised to the third power. Don't forget about the exponents. Now we can use the Nernst equation. So we have the first one. We're solving for all 3 parts here it wants us to, which is just kind of silly. I'm just going to solve for this one here, because we already practiced how to solve for Gibbs free energy before. And that would be, Gibbs free energy is equal to negative in F cell. So if we solve for this thing here, then we can plug it in and solve for Gibbs free energy. I swear that I try to write stuff neatly. I really do. All right, so we have the voltage of the cell is equal to the standard voltage, which is 2.23. Remember, guys, that's the cathode minus the anode. Let's learn objective 1. And then we have minus 0.0257 over 2 electrons again. Natural log of 0.0345 over 0.035. And the voltage of that cell then is equal to still 2.23, actually. It doesn't change it. I mean, these are very close in concentration, so it's not going to change it really at all. It's like a insignificant, a negligible amount that it's different. For number 2, it is something a little bit more in size. And that's because, first of all, I'm not going to do this problem, but I'll get the answer down. First of all, the standard voltage for this one comes out to be 0.02. So it's very, very small already. And then if we do all the calculations for the cell that we just practiced above, we end up with 0.04. 85 is the zinc. Yep, cubed. And this one also has a typo. This is supposed to be a 2. So apologize for those typos. Again, hopefully when you got lost on that one, you came to the video. Maybe I'll send an email about it too. All right. Oh, so this one I had put on my notes that it's learning objective 1, but it's actually not. We have here the anode, and here we have the cathode. So we can come up with the overall balanced chemical equation of this. So we have magnesium solid plus, oh yeah, this is a really fantastic one. I forgot about this one. Okay, magnesium with a positive charge. That goes to then magnesium with a positive charge plus magnesium solid. So this is really fantastic because we end up with our anode and cathode being the exact same thing. And since our anode and cathode are the exact same thing, we we'll still have a potential difference because we have different concentrations. This is just really, really fantastic that this works. So when we do our work, our cell voltage here that we're solving for, that standard voltage here that gets plugged in right here, the E with the degree symbol, is going to be 0. Makes sense, right? Minus 0.0257 over 2 electrons, again, are being transferred. And then we end up with natural log. This is going to be the dilute over the concentrated. And so that's how this ends up functioning. We have the dilute 0.24 over the concentrated 0.53. And I actually don't have an answer for this one. I had mistakenly believed that this question did not belong in this section. So now that you have all the work, you can come up with the answer. And you can figure that out. It should be a positive value. All right. Learning objective 3. We have electrolysis. This stuff is going back to like Gen Chem. We're going to do mole work. We're going to then convert to mass, all that kind of stuff. So first of all, to understand electrolysis, we're taking this barium chloride, for example, and we're putting it into a container. I'm just going to use a box, and it has a piece that comes out here, we'll say, and then a piece that comes out here, we'll say, and we end up with then a molten barium chloride here. So this is liquid. And then we end up putting electrodes in here. So we have, we'll say, an electrode here, and we add electricity. So this is an electrode, and as we add electricity, these things separate into the barium here and the chlorine here. So the chlorine escapes as a gas, the barium then is dumped out as a liquid and then turns into a solid. So what we can do is calculate how much of these things we should get. And this is actually the basis of our lab. Our lab is electroplating, and it's still the same concept, only rather than gathering pure samples of different elements, we're gathering, or we're putting one of these things onto a different one. And we'll do that in the lab. Anyway, when we have this here, can I get enough on there? I think I can. I want to leave this up here while I do this problem. So we have how many grams of barium metal are going to be produced. We first take the amperage times the time in seconds. So we have times 30 minutes, 1 minute, 60 seconds. That gets us 10,800, and that's going to be then amps times seconds. I guess this is physics stuff that I still haven't actually like learned very well. But from my understanding is that the label for this thing then changes to coulombs, which is going to be very important because we have Faraday's constant, which is 96,500 coulombs per mole. So if we have 10,800 electrons, we can figure out how many moles of electrons are going to be transferred, because this is for electrons. And if we can figure out how many electrons are being transferred, we can then figure out how much barium is produced. This is just so, it just fits together so nicely once you see the whole picture. It's just really amazing. So we have then, let's go through this, 10,800 coulombs, 1 mole of electrons is equal to 96,500 coulombs. Then in our half reaction for barium, whenever we have 2 moles of electrons that transfer, 1 mole of barium is produced. See how this is just so beautiful? It just works together. And then we can then figure out what 1 mole of barium is. And that is equal to 137.3 grams of barium. We're going to start canceling things out like bosses. Boom, 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 boom. There, that one goes away. There, that one goes away. End up with a value of 0.64 grams of barium. And so this is one of the ways that we can purify elements. We can take like a salt like sodium chloride and heat it up to extremely high temperatures, over 1,000 Celsius, and then add electrical current to it, and then we can separate the 2 different pieces. And then we end up with all of this work that we can do. Number 23 is the same thing, so I'm not going to go through the whole process. Oh, darn it. Okay, I have to go back to this one. We're too late in the game for me to restart the video. Normally I would restart it if I had made this big of a mistake, but I was looking at the wrong thing. This actually has 900 coulombs, not 10,800, which seemed like off. So then we would go through the entire process and get the same thing. So let me do this here. 96,500 coulombs, 1 mole of electrons. The answer is the same. I was just looking at the wrong coulombs thing. Then we have 1 mole over 2 moles. That's electrons. That's barium. And then we have, same thing, 137.3 barium. That's grams. That's 1 mole barium. So cancel all again. And we end up with 0.64. It's just this part right here. That one changed right there. Fix. And then the next problem actually is where the 10,800 comes from. So we go down here with silver. And we have, this comes out to be 10,800 coulombs. We go through the entire process, boom, 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 and we end up with a value of 6 grams of silver. So there's that. All right, now we can go on to the next one, which is essentially the same thing, only I want to show you the electrons and how that works. In that ratio step, where the electrons, so we end up with, here, I'll just write out real fast. Sorry guys, the bell just rang. We're going to get all sorts of announcements. We end up with, again, oh, this is the same value there, 30 minutes. Oh, it's because of half amp. Okay, yeah, so we end up with 900 coulombs again for this one, just like the first problem we did. And then we go through 96,500 coulombs for 1 mole of electrons. We have 2 moles of aluminum for 6 moles of electrons. So we're using that guy right there. We have 1 mole of aluminum is 27 grams of aluminum. We end up with 0.084 grams of aluminum. Last problem here. This is a data problem, so we have lots of different things to look at. It's not as hard as it looks, but we are dealing with gases, so we are going to need that guy right there. So we have the volume in the end for what we're going to be looking for. So we have pressure, we have number of moles, we have R, we have T, so we're going to be able to plug everything in there to figure this guy out. First we have to get the number of moles. That's the electrolysis part that we do, only this time instead of going all the way to mass like we did in the previous problems, we're going to stop at moles. So we have 1.5, let's see, if we go through the 1.5 amps times 4 hours, 1 hour is 60 minutes, 1 minute, 60 seconds gets us our coulombs, which is 14,400. Then we can go ahead and do the work with this like we would normally. 14,400 coulombs is 1 mole of electrons, 96,500 coulombs. Now this part here, I kind of skipped over a portion that we need here, and this you should be able to come up with on your own. We're doing the electrolysis of water. So here's water, we add electricity, it splits up into hydrogen gas and oxygen gas. Then we balance a 2 there and a 2 there. And so we could write out the different half reactions for this. And we can see here, I just want to do it this way. We have the hydrogen here, going to the hydrogen here. Starts off as +1, goes to 0. But there are a total of 4 electrons because there's H2 and 2 of those, so that means that there are 4 electrons being transferred there. Same thing for the oxygen, only it is being lost. So we have a -2 here to a 0 there, and there are 4 electrons there being lost. So here's going to be the gain, here's going to be the loss. Doesn't really matter, just as long as we can see the 4 electrons and then we see the mole ratio of them. So let's go back to the original, the problem here. We have 4 moles of electrons, and then we have 2 moles of hydrogen. That gets us our moles for that, which is 0.0746 moles of hydrogen. And because the ratio is 1 to 2, if we have the moles of hydrogen, we can get moles of oxygen. It's going to be just half as much, 0.0373 moles of oxygen. So we have those 2 different pieces there. Now we can plug it into Pivnert because we have our moles. Let's go ahead and switch over to a different color. Red, PV equals nRT. Our pressure is going to be 1.05. I converted this into atmospheres. And remember that this is something maybe you have to look up. 1 atmosphere is equal to 760 millimeters of mercury. 1.05 atmospheres times the volume is equal to the number of moles. We'll do hydrogen first. 0.0746 times the R times the temperature, 293. There's my temperature. Volume is equal to then 1.71 liters. Now we could do another problem for oxygen the exact same way, but we don't have to. It's a 1 to 2 ratio. The moles is half as much. If we plug in half as many moles here, we're going to end up with half the volume. That's the way that it's called Avogadro's law works. It's a 2 to 1 ratio, a volume ratio. So we end up with a volume of oxygen equal to 0.855 liters, half as much. All right, so like I said, this problem is really involved and looks difficult, But we have all the pieces. We know how to do a problem like this. We just have to organize the information to be able to get to that end point. So, don't be afraid of a problem like this. Just start in a place where you know you can get an answer, and then start building from there. If you take a wrong turn, try something else. All right. That is all we got for this one, ladies and gentlemen. Thank you very much. And actually, guys, that is the last one that we are ever going to do. So, well done. Good job.